Potential energy, kinetic energy, everybody's learned that stuff in school, right? And all you science teachers are like, oh yeah, boy, have I taught that. So, and we know in this situation, this is the classic thing where you have a pendulum, you have a weight, that weight has a mass, and if it's up here, up here it has potential, and down here it has kinetic, right? And if we assume that it is 100% transferred, is that the potential energy here is 100% transferred to kinetic energy here. Okay, this is, you know, no news for you guys. And we know that this potential energy is mass times gravity times height. And the mass we measure on the scale. And we know that the kinetic energy here is this formula, 1/2 mass times velocity squared. And we know that because this ball and this ball have the same amount of stored energy due to the law of conservation of energy, that we can say that those two are equal. And then we're just going to say that looks like an equation. So we're going to say mathematically that 1/2 mv squared is equal to mgh. And look, we have a mathematical equation, a relationship, and we can solve that for any variable that we want to get any answer out of it that we care to. And conveniently, interestingly enough, there's a mass on each side of the equation which we can just cancel. So eventually what we're going to do, and I'm going to ask you guys to do this, is we're going to solve that for v. Okay? So that's the first piece of the puzzle. The second piece of the puzzle is if you have a table that looks like this, and you have a ball that is rolling along here, eventually it's going to leave the table. Okay? And if it has a certain velocity this way, it's going to, if you were just to drop it, it would fall at a very prescribed rate. People took these measurements, did the graphical model, or did the mathematical model, and if you know where I'm going, you're going to see that the amount of time that it takes, so we're going to call this d, okay, and this is the formula, d equals 1/2 the acceleration due to gravity times time squared plus v0 in that direction times t plus d0. So this is the classic, you know, physics equation for any sort of falling object. And for us, we don't have any initial velocity in the vertical direction, so our v0 cancels out because we don't have any, it's basically at 0 in this direction. And then our d0 is just going to be d, and then if we're going to call this 0 down here, it's actually going to be a negative acceleration. So the idea is it starts at d, and then it eventually is going to drop. So we can solve this for t. So we're going to work through, and we're going to solve this equation for t. And what does that t mean? Time for it to hit the floor, right? Okay, excellent. And then at the same time, this thing is rolling along like this, and we're going to assume that it continues at 100% of its speed. So while it's dropping, it is also going to be doing this, and it describes a perfect parabolic shape. Okay? And we know that this distance, which we're going to call little d, is going to be what? If this is v, the speed it's rolling, it's vt. So it's the initial velocity, so little d is equal to the initial velocity times the amount of time it gets to do that, which is determined by gravity, right? So it's going to be vt. Okay? So here is the activity. Physics teachers, do you know where this is going? Yeah. Yeah, okay, so what we have is two things that we're going to use the vernier probes to do it. Over there is a bunch of tables with little chutes and golf balls. And the first thing we're going to do is we're going to put the vernier photo gate at the end of it, and we're going to shoot the balls, and it's going to tell us the speed of the ball as it's leaving the table. So we're just going to do this part. And then if you know the speed of the ball leaving the table, you should be able to predict using these two equations how far it's going to land. So the goal is to put a piece of tape out there, roll the ball, and when you roll the ball at precisely your V, it will land exactly on your piece of tape. It will hit exactly. So this is a classic physical science experiment. So that's the first project. The second project is we're going to take a piece of thread and we're going to tie it up to the light up there, and then we're going to have a bunch of golf balls with little eye screws, and then we're going to pick the golf ball up and just let it swing, and it's going to go and it's going to cut the string on a razor blade, and then it's going to continue on horizontally at V. But what is this V going to be? The V is going to be this V from this initial calculation. So your goal is to put a piece of tape on the floor, lift the ball to a pre-calculated height, let it go and have it hit the piece of tape. And if you get it right, it will work. I mean, it will land on the tape. It's amazing. So that is the project. And so we're going to do these in stages here. So I want to do this first one first. So the math is not that complicated, but how do you get the speed? Like, how do you know that? So I'll show you how it works with the vernier probe. So basically the idea is there's a little laser, and actually it's a beam of infrared light, and as things pass it, it will tell you various things. The one we're going to use is the gate mode, which is going to tell you the time that basically the light is blocked. You know, it's like, okay, it's blocked here, it's blocked there. So the idea is that if you measure the golf ball, the object, this is your D, this will tell you your T, then you can calculate your V. V is D over T. So you have to program into the vernier probe the length of your object, which is pretty simple with your with a ball, but with a sphere, you know, you have to make sure that the center of the sphere is going through, otherwise it measures a chord and not through the diameter, right? So that takes a little bit of messing around. And it's going to look like this. So this is pretty spiffy. So it's going to tell me, this is telling me distance, and if I do this through here, it will deliver data. That was a pretty quick run, okay? But for you, and I'll leave this up here so you guys can do it, you're going to have to change it to give you the information that you want, okay? So for us, we're going to go to sensors, photogate mode, and we're going to go with the gate. And then you have to measure the length of the object that is going to be passing through the gate. So you have to get out the calipers, measure the diameter of the golf ball. Okay? And then you're going to enter that in here. Okay? So the length of the object, let's just call it 3 centimeters for now. Oh, 30 centimeters. 30 centimeters, okay? So I'm going to go ahead and run it. It should tell me my velocity because it knows this distance. I'm going to pretend it's 30 and it'll tell me how long it's blocked. Bam. Oh, it's not all that exciting when you look at it, right? But there it is. Okay, that's my point. And it told me that it was 0.3 seconds and my velocity was 9.978 meters per second. So that's all we're going to use this for. Let's then bring that whole thing over here. So you guys come on, let's look at these tables. I'm going to suggest people who've used these vernier probes like be the team leaders. And here we go. This is what we got. We have a bunch of them. And we'll need 4 for the experiments. First steps, just to kind of speed up the process, you're going to need a couple of things, right? To calculate T, what do you need? You need this distance. And you need the acceleration due to gravity, which is 9.8 meters per second squared. So it's a mathematical model that predicts where a ball will land based on acceleration due to gravity, which is a quadratic. You could put the tape and then just do successive rolls and see if the one that hits the tape does exactly match the speed, or you can do it the other way around. You can, like, somebody can roll it, mark the tape, and you can say, based on my estimate of the speed, I think that's going to be 79 centimeters or whatever, and you can measure it and go, oh, sure enough, it is. So you can do either way. So then after everybody's had that experience and kind of familiarize yourself with this thing, set up the razor blades, and we're going to drop them, and then the height. we should be able to predict where it lands. So I'm going to suggest that you start with a hypothetical. Go back to your papers and actually start by measuring this distance using 9.8. Can you pick a velocity and calculate a d? Can you make that connection work? And then we'll come back and see if we can do it physically and use your model and see if it really works. So someone needs to get and measure this distance and then put a v in and see what d it gives you, and then we'll try it.
Okay, so we're dropping from.
You get the ball from that.
Or that's those two.
The amount of energy.
What's the height?
Let's just debrief that activity just for a few minutes. I mean, can you see that would be just like mayhem in your class?
Oh, yeah.
Right, it was, oh my gosh. But the thing is that, I mean, this is the absolute culminating experiment in that whole Newtonian, if you're not using calculus, this is sort of the super cool fun lab that you get to promise kids you're going to do for months, you know, and you lead up to it. There's a lot of anticipation. And then eventually they understand that it's kind of a big deal and they take it pretty seriously. And if you've done a lot of projects on the way and they already basically know how to comport themselves, well, my experience is the first time you ask a bunch of kids to stand up and do something, the first thing that happens is they all just start goofing around. Because they're like, what, we get to stand up and move around, you know? And all of a sudden, like, it just gets kind of out of hand. And so, but after a while, everybody like gets up from the table like, okay, here we go. Because they've done it 100 times, then it doesn't seem quite so chaotic. So, but a lot of what happens when you teach in this way, I found, is that you are training them to behave differently and have a different set of expectations about giving them some personal freedoms. And over time, they realize that when you stand up in class, it's not free time, it's actually part of the assignment, and they better get on it. And so they're not messing around as much as they are at the beginning. But I've just sort of like acted on the good faith that most kids, if you give them responsibility gradually, will operate pretty carefully and respectfully. Maybe not a room full of freshmen, but when I taught in the big school at Willamette, I mean, I would hand out a box of razor blades to my class of 35 freshmen, you know, and I never had an incident, you know, and I think it was just that mutual respect, like, all right, guys, I'm going to give you these, and I'm going to trust you, and pretty much it's worked out.
Did you give that spiel to us?
Oh, yes, right. Like, this is a contract, look at this, I'm going to hand these out, and we need to have no trouble, right, guys? And then, you know, it works out, okay. So far, I kind of see it as a mini like shop class. In a shop class you use all kinds of dangerous things. And for you guys who are not already the science teacher, just make friends with the science teachers, you know, like that's where all the scales and beakers and stuff is, you know.